Your phone is juggling two very different jobs at the same moment. One app is a live video call that cannot tolerate delay. Another is a background cloud backup that mostly cares about bulk throughput. Both want to leave the same device and reach a data network, but they do not want the same treatment. Here's the puzzle. If the network treated every bit the same, the backup could crowd the call, and the call could starve the backup. So, how can one device get two different kinds of network behavior without melting into a single, undifferentiated stream? Keep that question in mind. The answer in fifth generation mobile networks is not one bigger pipe. It is a carefully managed session for each kind of connectivity, and a way to steer each session into the right network slice. Start with the simplest move: split the problem. Instead of one shared connection that everything fights over, the device can open separate managed connections. In 5G, each of those is called a PDU session. A PDU session is the association between the user equipment, the device, and a data network. It is not the phone is online in a vague sense. It is a concrete, named relationship that the core network can set up, track, and tear down. That session can carry different kinds of traffic. The source is explicit. A PDU session may carry IP data, Ethernet frames, or unstructured data. So the idea is broader than just another IP tunnel. And here's the part that matters for our two apps. A single device may maintain multiple parallel PDU sessions at once. Applications are mapped onto those sessions. The video call can ride one session, the backup can ride another. You should now be able to see a PDU session as a separate managed data connection, not simply the phone's single internet link. A separate session is only useful if the network knows what kind of service that session is asking for and where it is trying to go. That is why every PDU session carries two identities. The first is S-NSSAI. Say it as S-NSSAI. It identifies the network slice the session wants. Inside it, you will find a slice service type, and optionally a slice differentiator when you need to pick among slices of the same type. Think of S-NSSAI as the requested route class: low latency, enhanced mobile broadband, massive machine traffic, or a custom service flavor. The second identity is the DNN, the data network name. That is the destination data network the session should attach to, like a named gateway into a particular external network or service domain. Put them together and you get the rule the architecture insists on. One PDU session associates with one S-NSSAI and one DNN. A common misconception is that a slice is just a pretty colored lane on a slide. In reality, it is a selected service context that can span the relevant parts of the radio access network and the core. The session is how a device claims that context for one application path. So far, we only have a wish. An application needs connectivity with a certain service flavor. Nothing is connected yet. Establishment starts when the user equipment sends a session management request. That message is the traveler knocking on the city's front desk. It carries the intent, including the slice information the device is asking for, and it forces the control plane to wake up and make decisions. Until this request exists, there is no session to select a path for. Notice the order carefully. We do not begin with a giant static architecture diagram and then sprinkle arrows. The request creates the need for control functions. The diagram should grow because something asked for connectivity. From this point on, every network function we introduce answers a question raised by that request. Who received it? Who will manage the session? Where will the user plane packets actually go? The first control plane answer is the AMF, the Access and Mobility Management Function. In plain language, the AMF is the coordinator that the device already knows how to reach for mobility and registration matters. When the session management request arrives, the AMF is the receiver that must figure out what happens next. The AMF does not itself become the long-term owner of every data path detail. Its job at this stage is to understand the request in context. including the requested S-NSSAI, and to involve the right session manager. You can picture the AMF as the city's front desk. It hears the traveler's destination and service class, then finds the specialist who designs routes of that kind. That handoff is essential. If every function tried to do every job, the architecture would collapse into one overloaded box. 5G separates concerns: mobility and access coordination on one side, session and user plane arrangement on the other. The AMF is the bridge into that second world. Next, the AMF must discover and select an appropriate SMF, the session management function. Selection is not random. The AMF uses information from the request, including slice identity, so the chosen SMF is one that can actually serve that S-NSSAI and the associated service. This is where network function discovery starts to matter. In a real deployment, there may be many SMF instances, each scoped to certain slices, data networks, or regions. Picking the wrong one would mean a session that cannot be properly authorized, charged, or anchored. Once selected, the SMF becomes the designer of the session. It will own the control logic for establishing, modifying, and eventually releasing that PDU session. Plain restatement: the AMF received the ask, the SMF is chosen to turn that ask into a concrete session plan. A plan is still not a path. The SMF now selects the UPF, the user plane function. The UPF is the actual data gateway. User packets will traverse it once the session is alive. Hold the distinction carefully, because this is where students often blur the boxes. The SMF decides and configures. The UPF forwards. One lives in the control plane of the session, the other sits on the user plane where bits actually move. When the SMF chooses a UPF, it does so with slice and topology awareness, again using information such as the S-NSSAI. A low latency slice might prefer a UPF close to the edge. A bulk internet session might anchor differently. The selection is how the abstract service class becomes a real forwarding location. After this step, you can finally draw a candidate route, device, through the access network into a chosen UPF and toward the data network named by the DNN. Now return to the two apps. Their sessions can land in different slices. Call them Slice 1 and Slice 2 on the diagram. Each session still follows the same establishment logic, but each is bound to its own S-NSSAI and therefore to its own core network slice context and a corresponding radio access network slice treatment. That is the visual separation the architecture is built for. Slice 1 might prioritize the video call with tighter latency budgets and dedicated resources. Slice 2 might optimize the backup for throughput and cost. They are not decorative lanes. They are separately managed service environments that can apply different policies end to end. Also remember, each PDU session links one S-NSSAI with one DNN and is associated with one core slice and one RAN slice context. Parallel sessions let one device participate in more than one of those environments at the same time without forcing every application into the same treatment. How does the AMF find a suitable SMF in a network full of functions? Enter the NRF, the network repository function. The NRF supports discovery of required network functions. Think of it as a directory. Services register what they can do, and consumers query for instances that match a need. When establishment requires an SMF that supports a particular S-NSAI or DNN, discovery through the NRF is how the control plane avoids hard-coded guesswork. The same pattern generalizes. As the system grows, functions find each other by capability rather than by brittle, fixed addresses alone. We introduce the NRF only now on purpose. Discovery becomes necessary the moment selection is real. Until the AMF had to choose an SMF, a directory would have been an abstract box on a slide. After that need appears, the NRF has a clear job. Selecting functions is only half of making a slice real. The selected S-NSSAI is also supplied to the access network and to policy and charging functions. That matters because slice behavior is not only which UPF did we pick, it is also how the radio side treats the traffic and which rules apply for quality of service, charging, and authorization. If the access network never learned the slice identity, the radio leg could not apply slice specific scheduling or isolation. If policy and charging never learned it, the session might get generic rules instead of the service the application asked for. So the S-NSSAI travels with the session context. It is the thread that keeps the request, the core decisions, the user plane anchor, and the applied policies talking about the same service. Misconception to kill here. Drawing two colored regions is not enough. The slice identity has to be distributed to the places that enforce behavior. Only after the session is established and activated does data transmission begin. That sentence is easy to skim past, and it is exactly where intuition goes wrong. Sending the request does not mean packets are already flowing. Selecting an SMF does not move user data. Even choosing a UPF is still preparation. Establishment builds the control plane agreement and the user plane path. Activation is the moment that path is ready for traffic. Then, and only then, the application can send data through the selected network slice, through the chosen UPF, toward the data network. Watch the payoff for our opening puzzle. The video calls session can now carry delay-sensitive media on its slice. The backup session can push bulk data on another. Same device, different PDU sessions, different S-NSSAI and DNN bindings. Different treatment without forcing a single shared fate for every bit. Zoom out and hold the whole argument in a few lines. Applications that need connectivity do not all share one anonymous pipe. They map onto parallel PDU sessions. Each session associates the device with a data network and binds to one S-NSSAI and one DNN. The AMF receives the session management request and discovers a suitable SMF, often with help from the NRF. The SMF selects the UPF and drives establishment. Slice identity is shared with the access network and with policy and charging so enforcement matches the request. Only after activation does user data flow. Broader idea, this is a clean separation between control decisions and data transport. The control plane answers who, which slice, and which path. The user plane carries the bits once those answers exist. One open question the same style of reasoning can attack next. What additional decisions would be needed if one application changed its traffic requirements while the session was already active? Session modification, reselection, and policy updates live on the far side of that question, built on the same foundations you just walked.